Good morning, everyone, and welcome to the last IFIMAC colloquium of this year, because next month we'll have the IFIMAC Day. Today we have discussed many different topics in this colloquium, but today we are going to focus on the soft condensed matter field, and for that I have here a great ambassador, Olivier Dauchot, that I'm really pleased to introduce you. Olivier Dauchot is a research director at CNRS, in particular at ESPCI in Paris. He focuses on collective effects. His research focuses on collective effects on soft matter. He has made great contributions to that, but currently he focuses on active matter, programmable matter, and platforming matter. And he considers also a very important part of research is outreach. So he's leading the outreach activities at University of Paris Sciences and Letters. But before, he was a group leader from the Instabilities and Turbulence group in CEA-Saclay, where he did also many significant contributions, especially in the study of jamming and legacy dynamics of granular media, to the study of chaotic mixing, and to understanding the transition to turbulence. So I give you the floor, and all of you please enjoy.
Thank you very much. Well, okay, so first there are two screens, and I will probably never look at that one. So if you want to move there, it's still possible, because you will enjoy better since then you will see what I point at, because otherwise I will be a bit in the way. I can try to move there, but okay. Second, don't forget to ask questions. It's always more vivid if you ask questions during the talk, and of course then I'm here all the afternoon, we can discuss that further. Okay, so I wanted to tell you about active matter, and especially I will try to show you what happens when you move from liquid phases to solid phases of active matter. And active matter is a field where there are a lot of interesting collective effects, self-organization, like we have in standard matter, except that because it's active, these effects usually are dynamical. So essentially, we observe dynamical phase transitions, and that's typically the things we are interested in. So these are all my collaborators here, Corentin Coulet in Amsterdam, Gustavo During in Chile, Vincent Delphin in Paris, and Michael Schindler also in Paris, and these are students that collaborate with this work. Okay, so let me first define what active matter means, because I know that it's over. No, well, I think we have an issue here. Put this somewhere. That's right. Yeah, well, electrical contacts. Otherwise, I will speak low. That's right. Okay, so so I know the department here is pretty large, and there's a bunch of hard condensed matter physicists in, and so I will try to convince you that part of soft matter is also interesting for hard condensed matter physics. At least there are a number of topics for which the tools of hard condensed matters are most welcome. Okay, so active matter is a matter of which the atoms are active units. So what do we mean by active units? We mean that each of our little atoms will be something that obeys an out of equilibrium dynamics, which means that the dynamics breaks time reversal symmetry, and the particle itself, so that doesn't make it yet active. This can be the case for many different systems. What will make it active specifically is that the particle itself, the atom itself, has a broken space isotropy. In the present case, I will take the simplest example where the broken space isotropy is just one direction, so you have one arrow that is designed in the particle. Your atom has a left and a right. Okay, now it can harvest energy from the outside, dissipate energy, and so it will produce work. And because there is this arrow, the work in some sense will be polarized. So typical example of this would be a walker. A walker is consuming energy, walks in this direction from tail to head. So it's polarizing the energy it's harvesting into some motion. But it would be the same for an engine that is creating a force in some direction. So the idea when you talk about active matter is to consider a large number of these units and being interested in the phase behaviors of this, the large-scale physics of it, like aerodynamics or like what you would do, like transport properties in these materials and so forth. Exactly what we did during all the 20th century with these little atoms here, except we want to reproduce this, at least use the same kind of tools to study, for example, this dynamics of birds, which looks like big droplets in the sky, but could be the set of thousands of robots, or even, why not, a field composed of grass fields. Okay, and again, we are interested in the collective properties of these systems. So that's the goal. So when you look at active matters around you, it's essentially represented by biological systems. So, and what you can notice immediately is that you can recognize this as a physicist phase of matter. So here you have a gas of what I would call a gas of mosquito. Here it really looks more like a droplet. You can see that there is a well-defined interface that because sheets like to be together, so there are attractive interactions, and I mean like a liquid, they like to be together, and so you have here a very strongly condensate phases. And here you have a tissue, and in this tissue you can see that the cells, well, they can flow in certain circumstances, but in other circumstances they will be attached to some reference configuration. I mean, typically I'm not flowing. I hope so, not too much, not on the time scale on which I live. And so you can consider this more as a solid. So in the past 28 years, there has been a lot of work that concentrated on gases and liquids. Actually, it started more with liquids, and then there were more questions, more fundamental questions that came back to the gas. You know, as physicists, when we want to address fundamental questions, we like the ideal gas or the ideal Ising model. And that's what we can do. And so it was demonstrated that in this system, there are really new physics, which is not so surprising. You break fundamental symmetry at the scale of the individual particles, so you would expect that something important happens at large scale. And the typical example of new physics that takes place in this system is that, for example, the mechanical pressure that you can measure, the force by unit surface on a surface that is inside the medium, is not a state variable. It depends on the potential that defines the walls. Okay, and this is something that we are really not familiar with. It's a bad news from the point of view of theory, because it means that we have to identify all the state variables if we want to describe those systems. It's also bad from the point of view of measure. For example, people who have measured pressures in cell tissues, etc., well, they have to understand that this depends on the kind of barometer that they use to measure the pressure. Then the liquid, the phase, this kind of liquid phase separations actually can take place even when there is no attractive interactions between your atoms, which is weird, because what we understand from the point of view of classical standard materials is that if you want to go from a gas to a liquid, well, what drives the transition, the condensation transition, is the fact that you reduce the energy if the particles or the molecules are close together, because there is an attractive interaction, and you decrease the energy, and then okay, the gain of entropy of the gas, you forget about it when the temperature is low enough. With this, you have understood all the melting, all the gas to liquid transitions. Here you have a gas to liquid transition. It is really a large-scale physics property. It has been studied both theoretically and numerically with very, very large systems that takes place in purely repulsive systems. And this is really because these systems are motile. And this is called motility-induced phase separation. I will not talk about this. And then what actually launched the topic is that if you take this collection of particles that I described before, and you put them together, well, then you have these degrees of freedom, which are the positional degree of freedom that we are familiar with in liquids, but they also carry this little arrow, this polarity that says in what direction they exert the work. So it's a bit like if they were carrying a spin, except it's not a magnetic spin, but they have an arrow on the head. And so you can also have interactions between the arrows. Now imagine you have a ferromagnetic kind of interaction between these arrows. Well, because the arrows decide in what direction they move, well, then the phase transition to magnetization corresponds to a transition to motion. And indeed, so what people have observed is a transition to collective motion in the system, which means that you can have an hydrodynamic flow without imposing any external gradient of pressure or any shear from the wall. So which means that your Navier-Stokes equation must be revisited. Okay, so that's just, and this has been done, and started as early as in 95. There were some equations that had the name Turner 2 equations, which is kind of generalization of the Navier-Stokes equations for those systems, which resemble them, but there is a bit of the taste of the Landau terms of magnetization in these equations because there is this transition where the arrows align. Okay, so what I want to talk about today is not to review all this, first it will take more than 1 hour, but to discuss what happens when you go towards dense phases and try to see, okay, what can take place now in active solids. So I will define more precisely what I mean by active solids, and what I will show you is a kind of flowing crystal, which is a bit strange. And the second thing is that I will show how you can have a kind of collective actuation, that is your crystal emits a sound spontaneously. Okay. Although the dynamics is overdamped and everything is linear. Okay, so that's the plan of the talk. We'll start with reviewing a little bit of collective motion, which will allow me also to introduce the kind of active system I used. We'll go to this collective actuation in elastic structure, and on the way we'll see this flowing crystal. Okay, so what are the actors? So you need to have these kind of little things that move by themselves, by taking some energy in the field. And I really don't want to have sheeps or mosquitoes, and even bacteria in my lab. I'm not a biologist. But I want objects that move. So one way of doing is to follow exactly the program of my introduction. Take a disk, then design an arrow. So here you can see I have designed 2 legs. I call them legs by analogy with the animals. And one is a rubber stiff leg, and the other one is a metallic one. And then shake this vertically. And what you will see, of course, is that instead of having a symmetric motion, you will have a motion that is oriented, and this is performing a persistent quantum walk. So that's just a walker. Okay, it takes energy from the vertical energy, and it can move in any directions. All directions are equivalent because the energy is injected strictly vertically. Okay. You can, well, this is good. You can have plenty of them. We'll see them. Then this is another example. This you can buy on the internet. It's called an X-Bud. It costs a few dollars. It has the shape of a kind of a toothbrush with little legs there and some kind of silicone rubber or I don't know what. And then inside that, you have a battery and you have the kind of little engines that you have in the very, very first generation of mobile phones to make them vibrate. And well, when this is for kids, but we can do physics with toys. You see, well, then you can have a lot of them and okay. So this is again another kind of animal. And the good thing with those animals is that they don't evolve, they don't have social interactions, so they are the simplest physical animal form. Okay, so Newton's law, because they are just this, we can apply Newton's law. So we have an energy source that is the battery, and then we have this polar vector n that is the tailhead asymmetry. So you write down the Newton's law, mass times acceleration, sum of the force. There is the propelling force that comes from the engine, so in the direction of n, some kind of damping, which is opposing the velocity, and then external forces, and we'll see what kind of external forces that we can have, or interaction forces. And then because this vector has some orientation and we live in the 2D space, there is an additional degree of freedom, which is the angle of this vector. And there is no active torque because I try to design this stuff in such a way that it doesn't spin to the right permanently or to the left. We could do that. It's another kind of active system. There is still some damping because if there is rotation, then it will have to be damped. There can be external torque, and I decide to add a noise. So this noise is not a thermal noise, although it's written in the same shape. It's a mechanical noise because you can imagine that this is not perfect, and when it walks, it's not moving strictly straight. I could also actually add a noise in this equation. Why not? When it happens, you can think about it very, very rapidly that this noise will just shake a little bit your position. This one will reorient you, and that because you are driven, this will be dominant. This is the one that will make your motion a bit erratic. The one that translates you a little bit doesn't matter so much. Yes? Yeah.
Can you actually control this noise you have?
Experimentally, you mean?
Yeah, exactly.
No, not really. So you here you have your okay, so that's a matter of design. So this one, for instance, not at all. We'll see that in the other, yes. So this one here, you have your battery inside. The battery actually will lose power after some time. So this is actually already an evolving animal, unfortunately. And for sure, you don't control the noise. Or let's say that it's connected to also to the self-propelling force, etc. Okay, so then you do a very, very simple experiment to test these equations. You take the guy and you hold it You hold it, but you keep free the orientational degree of freedom. So this is done by putting it in this annulus, and you see I drive it along the square of a corner. So if I drive it, it means I can forget about the first equation, I impose the motion. The translation motion is imposed, and I look if my second equation is correct, and I see something real, is that it reorients when I turn. Which means that this cannot be described by this equation, because this equation is agnostic to the motion. So something is missing. What is missing is a torque. It's a torque that is related to the displacement or to the velocity of the guy that is imposed by this hand. Where is this torque coming from? Well, actually from very basic symmetry consideration. You are trying to design an active particle, and you start from the most agnostic thing, that is a disk. Now, this disk, you must break the tailhead symmetry. So there is a front, there is a back. Okay? Then you have designed your polar vector. It's the beginning of life, should I say. But now imagine that for some reason, the velocity is not in the axis of the propelling force. Now, of course, because you design your particle carefully left-right symmetric with respect to the polarity, it's not left-right symmetric with respect to the velocity at that time. And the damping, which is here written as an integrated damping, is actually maybe the result of all these legs touching the ground, etc. But these are certainly not central forces. So it's a lot of little arrows that are opposing the velocity, for example, in this gray zone. And you can see that the gray zone is not left-right symmetric with respect to V. And so there is a torque. And you cannot avoid it. All walkers have a torque when they are not aligned with the propelling force. As a matter of fact, this little guy here, so this is the little disk I showed you at the beginning. So it's only 5 millimeter diameter. What you can see here is the black dot here is the back, is the signature of this rubber that is behind. And so it's shaken and it's confined in a 1D channel. What you can see is that, well, it's moving on the more or less as it can. It's not, and now I'm going to push it. And now what you can see is that the black dot is systematically at the back. So also this one actually has this torque, which is not surprising from what I just said. It's just that it was a little bit more difficult to notice. Okay, is it important? It's always a good question. You know, when you do microscopic description, at some point, we want to do large-scale dynamics, so we are going to put under the carpet a lot of things. So is that one that we can put under the carpet or not? So if you take standard model for active matters, what people do, they were inspired from Brownian motion. So you take a Brownian motion and you bias it in such a way that it's not Brownian at equilibrium anymore and it's active. And the easiest way to do this is to add correlation in the noise that are not in the damping. If you do this, you break the balance, you're done. You have an active propulsion, noise with correlation. This is an active, so-called active Brownian particle. The first thing you do when you're a physicist is the harmonic potential. So you take this particle, put it in an harmonic potential. And when you do this, if the particle was an equilibrium Brownian particle, well, put it in a potential at a given temperature, the probability distribution of its position would be exponential minus beta the potential. It means if this is an harmonic potential, you would see a Gaussian centered on the minimum of the potential. Here, what you see, let's say this potential is 2D, is that the particles climb in the potential. Don't forget that it has this force, so it climbs in the potential. And then it arrives at a certain distance from the center where the potential force and the active force compensate. It's just shifted, and then it will be at some position at some distance. And then because there is nothing on the angle but noise, well, it will diffuse pointing upwards around the potential. And this will be the density distribution of this for the position of the particles. Let's do this with this little guy. So as an experimentalist, you buy this little guy on the internet, €3. Then you want a parabolic potential, you buy a parabolic antenna. That's €30. And then you put one in the other. When the battery is low, very low, this poor guy here has not much energy, as you can see. After some transient, what you do observe is that it indeed climbs in the potential and then points outwards and then start to diffuse like this. Exactly what I described here. But any kid will tell you, come on, that's not what's supposed to happen. What will happen is this. If the battery is strong, it will orbit. And you cannot get that from these equations. You need the torque I was mentioning. So I will not enter into the detail why you need the torque, but it's really very basic calculations, right? You can even study the non-noisy dynamics. You can just do Newton equations, you integrate, there are 3 degrees of freedom, and you indeed find, so this is experimentally the two regimes, the regime where you point outward and you diffuse, and the angular velocity is 0 and just diffusion, and the case where you orbit, because there is noise, you can actually shift the direction of the orbits, and the angular velocity is always 1 or -1, let's say. You take your equations, write them in a more dimensionless way, but it's exactly the same equation, and you reproduce the two dynamics with no surprise. You can analyze the phase diagram, and essentially the phase diagram tells you that you can go from orbiting to a climbing solution. So the orbiting one is the most natural one, I would say. And this will be essentially controlled by the two time scales that are in these equations. One thing to note is that the inertia does not play a very important role. The transition is always there from orbiting to climbing. And what the inertia does is that it creates some kind of, from second order to first order behavior at very large inertia. So the systems that we are going to consider today, they have inertia which are sitting between 0.1 and 1. So it will always be a very simple supercritical or continuous transition, bifurcation. Okay, but that's one gap. So now we move to n gap, because that's what we are interested in. So the first thing to do is to put n guys in the lab, and you want n to be large, not 10, not 100, but a few thousand at least. And the few thousand battery to change every 2 hours is not the thing you really dream of, whether it is for convenience or for the environment. And so it's better to work with the little guys that you shape. So let me speed this one. Let's see what you observe. So because you never know, it's experiments. So when you shaking strictly vertically is actually quite not such easy task. You can always induce a little bit of lateral forcing, and given what we're going to observe, we want to be sure it doesn't take place. So we also have these purely isotropic disks. So these disks are perfectly symmetric. So from them we expect, of course, they are non-equilibrium, but let's say standard behavior. And indeed, you shake them. These are not simulations; these are experiments. And they are colored by the orientation of their move. When you shake them, these ones, you see what I would describe as a liquid of hard disk. And here, it's exactly the same number of particles. You see that it's completely different. There are very large density fluctuation, big holes, and they move. And when they move in these clusters, they seem to move in the same direction. You can quantify this by looking at, so in this experiment, what we control is indeed the noise. So you need to shake to get some velocity, but typically for all the amplitude of shaking that we use, the velocity is essentially the same, doesn't change, but the noise on the particle increases when we increase the vibration amplitude. And so here, when you increase the amplitude of the vibration, it also means we increase the noise. So here we have the probability distribution function of the magnetization. Let's say it's the magnetization. For the systems at low noise, at large noise, it takes low values, and then at low noise, you can see that the distribution shifts to larger value. So this order parameter here is growing from large noise to low noise, and by contrast, of course, this one doesn't see anything. Okay, you can look at correlations, spatial correlation, temporal correlation, all your favorite tools, and they clearly indicate that something happens. Here you have these convex in log scale these correlation functions, and they turn to something that is concave. Obviously, something is taking place somewhere. All this is, of course, full of finite size effects because the system is not the size of the universe by far. But clearly, something happens. So what we did, to make the story short on that part, we took the equations. We mapped all the parameters on the microscopic dynamics of single particles and binary collisions, which took some time, and then we simulate the equations. So it's really an extension in silico from what we observe in the experiments. And this is what you get when you do periodic boundary condition. Let's show it again. You see that you really have a macroscopic flows developing with all particles essentially moving in the same direction. You can study the phase diagram. And for the experts, for very large systems, you even see regions where you transit from the disordered gas at low noise, at high noise and low density to this polar fluid at large density and low noise, and in between there is a regime where you find these traveling bands, which have been observed and which have been claimed from the theory to be one of the hallmark of this transition to collective motion. Yes. That was a terrible word. So you take a very dilute system and you analyze the trajectories, but all the statistics, that is the probability distribution of the displacement on the time scale on the time scale, let's say delta t, where delta t is the time between the acquisition of two images, and then you increase this lag time, so you have plenty of statistics for the displacement on different lag times. You do also the same for the angle. Then you look at the correlation between angle and displacement, and this gives you plenty of curves. This is just for the gas, single particle. And then what you do is you do an optimization for the 1, 2. So there are 1, 2, 3, essentially 3 parameters plus the one. So for the moment, no interaction. So you do an optimization to find these 3 parameters that maps all these curves at once. So it's not one by one. And it's extremely reduced the range of parameters you can use if you want to map all these curves. So then you say, okay, these are the parameters that we get to the experiments. You are missing one, which is the one about the interaction. So then you look at collisions, and you play essentially the same game just for that one. So that was a big work that was done with Erwin Frey and Christoph Weber. And then we run the simulation and we observe this. And then to do that, what you do is that you set, you say d equal 1 by reference would be the experimental conditions. But packing fraction, that's easy. This we can measure and control. And then you just tune one parameter, and the others will be context. Okay, so this property, what is interesting to notice here is that it's only disks. And so the only thing that we have is these disks that collide. They have no reason to align themselves because of their shape. They are just disks, and it's really elastic collisions. There's almost no dissipation in the collision. It's a hard metal. But they have this property of this torque here. So the conclusion is that this self-alignment with collisions produce, at the large scale, an effective ferromagnetic interactions between the little spins, the little arrows, and produce a transition to collective motion. Okay, so can you understand that? So there we do a little bit of theory. So my talk will always be a mix of experiments and theory. So we do a bit of theory, and since this can happen in the very dilute regime, we can do kinetic theory, assuming that it's a rather dilute gas, and see if we can understand something. So I will not go too long into that, but just to show you that we can do that. First, what is the mechanism? The mechanism is easy to understand. Imagine you come from the end of not the end of the universe, and you never encountered anything. So what happens is that then, by this equation, you can see that your velocity has relaxed towards the direction of propulsion. There is no minus part. Towards the direction of propulsion, which is normal, right? You have an engine that moves you this way. There is nothing else. You move in that way. Okay, and then you collide with a wall. And then if you collide with a wall, just after the collision, the velocity, of course, is symmetric to the one you had before. So, okay, your bounce essentially obeying the elastic collision rules. But you have not rotate n, because it's just an elastic collision. So the elastic collision doesn't say anything to the orientation. So now you are with an initial condition where n and v are not aligned. Okay, n and v are not aligned. So now this term is not zero. And now you have two equations with two time scales. This one tells you how fast v is going to realign on n. This is how fast you will adopt the motion driven by your orientation. And this one tells you how fast n will rotate towards v. That, remember, in the experiment when I was driving, is typically what distance you have to do to reorient your hand. Without surprise, you can compute, essentially what you need to compute is how much do you gain in momentum at each collision. So you have two guys that come in, they have a certain total momentum. After the collision, I forgot to say something. Look, the result, okay, sorry. Let's finish with the manual explanation. So you collide, you bounce. And so you see now these two are rotated towards each other at different pace. So v will always rotate to the right, because this is towards n will rotate towards v. And at the end of the day, when both relaxation process has taken place, V and N are again aligned, these terms cancel, and you go again to the end of the universe as you can. But you see that the angle that you had with the wall at the beginning, and the angle that you know that the trajectory is now making with the wall at the end of this full scattering process, this one is much smaller. So you somehow align with the wall because of the relaxation process. So it's not in the collision, it's in the relaxation process. So it's the full scattering event, defining the scattering event by the fact that all the process have to be relaxed, which is a good way to define the scattering event, by the way, in any field of physics. Okay, so this is the scattering event. You come with some, of course, this is an easy picture. In practice, you have to consider that there are plenty of different kinds of collision. There is the cross-section. I mean, we all suffered cross-section calculation when we were at school. And then you come back to it and you say, oh no, but yes, you have to. But you can do that. And you sample over the Boltzmann measure for collisions of hard disk, which is known, except that the property of each collision is not conservation of momentum, because there's no reason to have conservation of momentum here. Some collision will increase the momentum in the direction the momentum had before the collision. Some will destroy it, and then you have to sum all this and see at the end, does it produce some net positive effect or not? And the answer is yes, depending on the control parameters. And that's what you find here. This is alpha. Alpha is the ratio of these two time scale. And you see that for alpha close to 1, there is a region here where you will drive the transition to collective motion. So that is, you will create on average momentum over the collisions. And of course, if the noise is too large, you destroy it. I think it's interesting to notice that it's around alpha equal 1, which means really the physics is the competition between these two time scales. And this is just a simulation showing you the transition from one to the other. Clear? Questions? No? Okay. So let's increase density. Yes, question.
It's one from the beginning. So the torque you see when you
yeah.
The torque you see when you put the hex back in the system. That torque is present whether it's active or not. No? If you turn out the battery, you still see the alignment.
Yes, it would be. The only thing is that you still need to have a polar vector, and you still need to move it. Yes, you can turn off the battery, it doesn't change.
And I was wondering, would you have this, instead of inputting this torque in the equation, would you have kind of space dependent friction coefficient that tells you that one of your legs is
but then you have to make a more microscopic model.
Okay, yeah, you have to consider
exactly, and we want to do, central body forces, etc., etc. Yes. So somehow this model is already an effective model of the microscopic dynamics of when you don't always do ab initio when you do quantum mechanics. That's exactly the same answer. Okay, so let's go denser. So I think it's not here that I will recall you that the transition to crystallization in 2 dimensions is a bit weird for this. This transition actually deserves a Nobel Prize to the authors who studied it using the renormalization group techniques. You start from a gas of hard disk, you go to a crystal of hard disk to this exotic phase. And because you are 2D, you never have true long-range order, even in the crystal crystal phase. And the transition is very much driven by the defects that are building up because of temperature in the solid phase. Okay. So what if we are active? Very simple, because if you're active, I just have to compress my particles and to increase the density. The first thing that we see is something quite different. This is just a static picture. And what you can see is that when I try to make this system very dense, what happens is that I form clusters of particles that are actually close packed. They are at packing fraction 0.91. Yes.
These particles are
The disk, the shaken disk. And you just compress, or more precisely, add more and more in the given setup. And you find these clusters that are already close packed. And when you increase the packing fraction, what you see is that the distribution of the size of the clusters suddenly get a bump, which is a cluster that is the system size, and a parallel distribution of the size before that resemble a lot a percolation like of a cluster that becomes the system size. Okay. You can look at the kind of order that you have by looking at this order parameter, which is called the exotic order parameter, that tells you, okay, how much this lattice is ordered in terms of orientation of the bonds of the lattice. And again, when you increase the packing fraction, but note the value of packing fraction. So here we would be in the exotic phase at equilibrium. Actually, would already be just above. Well, for sure, there is some kind of exotic regions, but it's not at all exotic. There are a lot of disordered regions. And indeed, we see these clusters and they grow, and then you get a system size. But then what's crazy is that 0.80 would be really in a well-formed crystal into. And here you still have this kind of coexistence between these zones. That's another picture of that. You can look at the pair correlation function to see, okay, how much ordered is that? And the pair correlation functions indeed have sharp peaks. And something interesting is that if you look at the position of the peak, when you increase the packing fraction, from the very beginning, packing fraction, even here, you see when you have these very small clusters, the position of the peaks does not shift. That is, what it means is that when you compress your system, the part that is ordered is already at close packing. It's not like if you have a crystal and then you can push and condense your crystal furthermore. You cannot. The crystal you form so it's really looking like a first order phase separation between a close packed crystal and then as a result a very dilute phase because you immediately go to close pack. Is that picture enough? And then we could try to understand it. Well, let's look at the dynamics. If you look at the dynamics, that is how much the particles move in a typical timescale tau. So this is the mean square displacement, or the square root of the mean square displacement. This is in units of the particle size. These are from different packing fractions corresponding to these curves here. So the blue one is really here, actually in this phase. Well, what you see is that it moves. This is always moving and it moves 10 particle size. So whatever the slopes, this thing is not frozen. This is not a plateau. But this one for sure, I'm sure it's not a plateau. And of course, this could be tricky because we are measuring the mean square displacement. It means we are summing over all the particles how much each one is moving. So if all those ones are strictly static and those ones are moving like mad, you could get these curves. Because maybe you are just measuring the ones that are moving. But of course, I mean, people of liquid state theories are aware of this, and so you can compute something which is called the dynamical structure factor, which is more something that tells you what is the fraction of particles that, let's say, has changed its neighbors or has not changed its neighbors. So if the picture I just described was true, then this should always remain finite at some point. And here what you can see is that, well, of course, the time scale of the relaxation of the structure is increasing, although not like a glass, it's not several orders of magnitudes, certainly not like in a crystal, but on top of that, it always goes to zero. That is that on the end, everybody has moved. Okay, and when you look at a movie, then it's obvious. Because what you see is that the defects are extremely mobile. And they travel and relax all the structure of the system. So the activity of the particle in the crystalline phase somehow transforms into an activity of the defects themselves. Okay, so that's the phase diagram, active liquids. Here we have a liquid of clusters, and now here we have this kind of percolated, exotic ordered, but non-frozen clusters. And we are at a packing fraction of 0.84. The close packing is at 0.91. So there is a huge range here. What's going on there? I want to push. I want to go to the crystal. At the end, the disks are touching. The disks are touching, they should not move. We agree on that. So something must happen. So we designed hexagonal arena so that we map the crystalline order. And so we can put exactly 1,141 little guys and they touch. And indeed, then when you shake either those or those, nothing takes place. They are really touching, there's no place, no motion, nothing. And then we remove a few particles. And when you do this, you create what is called geometrical frustration. So even for this system that mimics well equilibrium, you create this kind of defects. You can see here, blue and red means that you don't have the right number of neighbors. Let's not focus on that. You remove some more particles, the type of defects change. All this would interest solid state physicists for years. And then when you go here to 1027, you again have a perfect crystal. The packing fraction is still very high, so this is not surprising. The only thing is that this crystal is not at its densest possible packing fraction, and there is no more geometry frustration because what happens is that I have removed exactly one layer. Okay, and now let's look at these guys. At the beginning, it's the same. But starting from here, already 0.89, so very close to close packing, the story is very different. We have again made defects, and it seems to be a real mess. So the system is already melting because of a plethora of defects at packing fraction as high as this. And again, here the system is finite. Might be that this would happen probably up to here if I was taking an infinite size system. But again, what about the dynamics? They did align. So not only they move, but they successfully align and form a coherent motion in the crystal. And that's the most mesmerizing part of the story, is that remember that for aligning, you need a scattering event with a relaxation process so that there is an effective alignment. But here there are billions of collisions taking place in a second. So how do they manage? I don't have the answer. The fact is that although the relaxation process does not take place fully, the alignment, the mutual alignment takes place, and they successfully align. And this is where I was wondering whether I was not a little bit forcing my system experimentally. And so I do simulation because I know that I can mimic the system. And this is a simulation exactly in the experimental conditions. It's not a very pleasant simulation to run. Imagine the number of collisions you have to deal with. And after a pretty long transient, the movie is pretty accelerated, you do see what we see in the experiments. So they do align. If you start thinking a bit about it, this is solid body motion, because otherwise there would be shear, and so it would not be ordered. They never change lines. So these ones are making the whole travel here at the same time as these ones, and at the same speed, but this path is obviously much smaller than that one. So what's going on there? There must be shear somewhere. The shear is actually taking place exactly along these fault lines. Layer by layer, the system accumulates exactly the right amount of shear at each line. And then I said, okay, we have simulations. Let's go quantum. I'm joking, but let's suppress fluctuations. So no more noise, or only 10 to the minus 15. And packing fraction as high as we can in this system to still observe the effects. And there you have a phase that is fully perfectly periodic in time and space. No more bad defects like here in the center, and the system is rotating. And of course, the question is, does it resist? It looks like really a flowing crystalline phase. From the point of view of crystallography, it would be some kind of a symmetric, in the sense that it's perfectly ordered in this direction, long range. In this direction, there are these defects traveling, so probably it's quasi long range. It's a kind of a bizarre active liquid crystal, a bit symmetric, if I want to be really rigorous. Does it survive large scale? If I make now simulations like crazy. So here is a simulation like crazy. So here there is 30,000 particles. We already see that something takes place in the corner, and then after a constant, the system does organize, it does rotate. Of course, it can be left or right. I will show you maybe left, but we have both of which standing runs rotate. And there is the central region that cannot really adapt. But what is nice is that when you increase the system size, so this is going from black to red, actually the fraction of the system, here this is normalized by the system size, the fraction of the system that rotates becomes larger, and it even rotates faster. So I think it survives large system. Still, you need confinement. So large but confined. Okay. Yes. Yes. If we have time at the end, I will show you. We try the triangle, so just to lead you a very big triangle. The system makes an hexagon inside the triangle that follows that dynamics, and then needs triangle to make a really big, we go more hexagon, and at the end, we always have more triangles that will move. And then we at that point to the figure is equal to Okay, and so now I say, okay, but now I want a solid. And a solid is not something that flows. Here it's a solid in the sense that it's ordered, but it flows. I don't have a reference configuration. I would like a reference configuration, and now I'm going to trap there. Okay, and for this, because these little guys with 4 millimeters are really not so nice to handle, I will again deviate at the cost of not having very large systems. Okay, so what do I want? I want the third book of the kitten, the third page of the kitten, that is a solid, which means ball attached by frames, with funnels and these kind of things. But I want an active system. So I want particles with power. So naively, this is what I want. And I want them to be free to rotate. So why do I think something interesting could happen? Why do I insist so much towards the solid? Is because these things now, they have a reference configuration, they will exert forces on the springs, and so they will develop stress and strain in the system. Stress and strain is a tensor. It's a tensor living in the same space as the field, the vector field of the different forces. When a tensor lives in the same space, physical space as a vector field, it turns it. So there should be interesting coupling coming from there. So there should be a feedback. But okay, will it happen in a given experimental system? So what we did, we took net bugs, we put them in the same kind of annulus that the one I was using at the very beginning, and we can attach them by plate. As simple as that, and then we have the lattice we want. And we can do whatever lattice we want, and because we like triangular lattice, we start with triangular lattices. What are the control parameters of the system? Well, there is something that we all know is elasticity. So the guy here is off. I switch on the engine, it pulls on the spring is elongated by a length proportional to the force. That's all fine. Then there is this realignment mechanism. So that if I move the guy from left to right, after some distance, it will have rotated. This would be an alignment length. It could actually be a time rather than a length. It happens it's a length. And this will prove this from the Okay. So 2 lengths, 1 ratio. This should be the control parameter of this physics. So let's start. And so we build our system, we put it on the floor. It starts to be quite a big system because these X-balls are 5 centimeters. You want a number of them. So we put it on the floor and we don't have a solid. The guy goes away. So you have to run after your experimental system. Bye-bye. Okay, then we say, yes, but there is the guy inside. So actually, the symmetry, the translational symmetry is always broken. There is always the guy at the center that's pointing in some direction. Let's remove this guy. So we remove it. But still not a solid. Or it's a bit of a weird solid. On top of that, this is metastable. If I give a little kick, it goes in translation, as you can see here. Okay, so there is coexistence of these 2 dynamics in the system. Okay, now what is nice is that, okay, it's a solid in some sense because the reference configuration is only translating or rotating. These are the 0 modes of any solid. We know that if you want to do solid state physics, these 0 modes, we could forget about them. And usually we do it because we say, okay, we can attach the solid to the ground. And then here, what you can see is that actually there is not much extension of the links. Once the things are moving together, it's really solid body motion because it's those 0 modes. And so you can say, okay, but even if the springs were rigid, I would see the same. And indeed, we did it with little sticks and you see the same. And so because it's rigid, there is no elastic deformation. You can go to this infinitely rigid limits. You go in the equation. This takes some time. And you find that you can map this on a free energy problem, which is quite surprising. It comes from the fact that if you look in the equation on the angle is actually an equilibrium Lorentz equation. It's only the propulsive one that is not. And because here we are in this infinity rigid limit, the propulsion just guarantees that the frame of reference moves. Because once you have this inside this frame, it's equilibrium. And so we can actually see, compute the metastability, etc., etc. I think it's nice. I mean, it's not so frequent that we can do exact calculation so far. And it actually demonstrates that in this case, this is a mean field XY problem. So there's a true transition to for a model to order because in mean field we are familiar with the fact that everything order takes place. Even okay, but I want a solid. You will remember this from my head. So I will pin the boundary condition. So now you don't go away. I am also this in the lab. And so, okay, so when the springs are stiff, so I cannot tune the engine of these X-bugs, as you could understand. So I will tune the stiffness of the springs, but that's the same. At the end, I would have a small value of pi. It means the springs are stiff. The guys, they cannot push very much. And so they are shaking this lattice. Of course, these are not standard phonons, because this is our equilibrium forces pulling and pushing, interacting. And it will be interesting to study this phase. And that's what I wanted to do. But it happens that when you increase the control parameter by taking softer springs, you see something that drove me away from my first motivation, is that they do this kind of collective actuation, that is, they actuate some modes in a very, very specific way, in a very ordered way. And all the guys are oscillating more or less in phase. Okay. Now, if you look at this experiment, the deformations are big. I mean, look at the springs. They are deforming a lot. This one is even bending here, etc. So it's not clear that linear elasticity is a good framework to describe this. So the first thing we did was to take the equations, go in the overdamped limits. The X-bugs also have some inertia. They are 5 centimeter particle moving 10 centimeter per second, a little bit of inertia. Let's say there is none of this, just to know. And let's make the harmonic approximation. That is, we will replace the lattice by its dynamical matrix and simulate these equations. That's exactly the same, but with this very strong hypothesis. And we do observe the same. So it's not the nonlinear elasticity that matters here. It's not inertia. Doesn't mean there is not here, but it just means it does not matter. So we can at least think in that framework. Okay. So we have the synchronized chiral oscillations, which are rooted in the only nonlinearity that remains, which is this term here, this famous torque that I introduced in the beginning. So here it plays a crucial role. It was already, but here it is the core of the problem. Okay, so let's analyze this a little bit more in detail. We project the dynamics of the modes. Now we are doing solid state physics, so you have the modes have class of symmetries. You go back in your Cristallo favorite book. And what you see is that the energy condensates on a few pairs of modes. They all belong to the same class of symmetry, so these are somehow generalized harmonies of these two. But the modes that are selected are the two lowest energy modes. Okay, that's not so surprising, these two. But of course, we can change the lattice. So here, this is a Kagome lattice, and we can reproduce the analysis. And here we find something more interesting, is that again, it condensates on pairs of modes, again belonging to the same class of symmetry, but it's not the lowest energy one. So it's not that you do your dynamical matrix, diagonalize, put the modes, and then pile up the alpha omega. That's not as easy. Here, the geometry of the modes matter. They must come by pair, and they must something. You don't know what. They must something. So by examination of a number of cases, what we got from the experiment is that they like to be extended modes. So on the nodes of the modes, there should be arrows as much as possible everywhere. They should be locally perpendicular. The system likes to have polarization of the two modes that are locally perpendicular on each node. Okay, can we understand that? Let's see. So, but clearly there is a non-trivial mode selection, which is rooted in the geometry of the modes. Some more information. Okay, you have a new phenomena, so you run different experiments. We change the pinning conditions. So here we pin it in the center, and the center cannot rotate either. So there is a restoring torque from the springs. This is a bit painful to model with a standard lattice, because if you do this, then of course there is a zero mode, which is the rotational mode, because these are only point force. So you have the zero mode. But it doesn't matter. You take the equation in the mode space, you stiffen the zero mode by putting some eigenvalue which is not zero there, and then it's almost this. And then what you get is the same dynamics as this. See here, I don't know why this video is so slow, because this is not reverse. And it rotates, but you're not, and then I should check this one. Okay, anyhow, we can analyze the motion, and then what we see is that the system condensates on these two modes. One is the rotation mode, and one is the linear combination. One is a linear combination of the two translation modes. So again, there is a condensation of two modes. That's what I want you to remember. And we tried several lattices, and always the system likes to select two modes. Okay. What else? Well, you can tune pi continuously, and when you tune pi continuously, we see that here we have this disordered regime where the guys are pointing in all directions. And here we have this collective actuation, but I didn't tell you what was going on in between. Is it a nice transition or not? It's a normally messy transition. So if you look at, so these are the nodes which are colored, and this is the rotation frequency of each node. And indeed, when you are in this collective actuation regime, well, they are not all equal, these frequencies. This is a zoom on this. They are not all equal. If you look at the spectrum, you can see that they are not exactly the same for all the nodes, but the nodes, you can categorize them by class. But what is clear is that everything is driven by one frequency and all the others are a rational fraction of the first one. So at the end, it's a pairing portion. Okay. When you enter this zone, when you decrease the control parameter, what happens is that some of the nodes, they cannot follow, and they fall down. And because you see up and they fall down in some sense, the frequency, they revert or because of the noise. And now you have a continuous spectrum. The line becomes completely chaotic. So that's not nice because you don't have a nice transition from something where you have a zero order parameter and then something continues to an oscillating behavior, which then have to capture with some kind of a hot bifurcation. The situation is more complex. You go through the chaotic regime before stabilizing the periodic one. Good. Okay. Large system, we do simulation to study large system because this will take the place of the room. Large system, what we see is that indeed collective actuation resists, but we can see that it doesn't take necessarily place everywhere. There is this region here that does not follow. We can extract the profile of the frequency, and what we can see here is that when you decrease phi, you can have everything rotating at very large phi, like 5.5. But then when you decrease, somehow there is a boundary layer on the right, well, on the side of the lattice that stops. And progressively it decreases. And what is interesting to notice is that the way it stops is because the center stops rotating. So the frequency slows down, and goes to zero, while the fraction of the eye remains finite. So at the end, you have a core that progressively stops, but it remains actuated until the end. Okay, so now we have all facts and we want to understand something. Okay, that should, right. So we want to understand this. I will not go through all of it, and we don't understand everything, I will be clear. But one particle is easy. So one particle, we have already the phenomenology of the actuation. That is, after some point, the guy enters these orbital solutions. Because it's one particle, we can study it in detail. And I point at this for the following reason, that you can look at the equation. Okay, and these equations are very simple. You see that the fixed points here I write them without noise, correspond to the case where u dot equals 0. It means this is when the displacement and the active force balance. And as soon as u dot is 0, of course, the second equation is also 0. So you have an infinite set of fixed points, which are the guy pointing in any direction. Actually, the same problem as the parabola of the beginning. Now, you have this infinite set of fixed points, and what happens at the transition towards the collective, well, not yet collective, towards the oscillation, is not a hot bifurcation. And that's important, because usually in physics, when we have oscillation, it's a hot bifurcation. You do a linear analysis, and you have an imaginary part that goes positive, a real part that goes positive, with an imaginary part of your eigenvalue that's non-zero. Okay, that's a very standard scenario. It's responsible for 90% of the waves in the world, etc. Here, what happens is different. You have this infinite set of fixed points, which means in the displacement plane, you have a circle of fixed points. Okay. And then what happens at the transition is that these fixed points, because it forms a continuous set, are actually all marginal. You can always move from one to the next one. So there is always a zero eigenvalue. And what happens at the transition is that you start rotating along this manifold at an infinitely slow speed, zero frequency. And then the frequency grows continuously from zero. This is what you can see there. So this is very different from Hopf. Okay. And particles. you start with linear stability and you hope that it will remain something from what I just said. It's not the case. It's much more complicated. I want to wrap up soon. It happens that they don't, you have n particles, so you have n infinite set of fixed points, and unfortunately, they don't all destabilize at the same place because of the couplings. So this is tricky, and I will not go too much into the detail, but we can study it. And when we study it, what we find is that for low value of the control parameter, you have all your fixed points are stable. Okay. For large value above this bond, you can demonstrate they are all unstable. And in between, a fraction of them is stable, and it's a decreasing fraction. This you can compute. And then you can start looking at, okay, in this calculation, what is the operator that is coming in? When you look at the detail of this operator, you realize that the system wants, the most unstable fixed points are those which correspond when they are projected on modes, which will project maximally on pairs of modes that are indeed perpendicular and maximally extended. Is that proof of anything? No, because unfortunately the transition is not a continuous one. So the linear stability, the spinodal analysis, if I try to use words from other communities, tells you very little about what is going on at the bimodal. But at least even at the spinodal, there are the ingredients of the selection that we observe. The nonlinear problem, well, that's even worse, but at least we can look at the dynamics projected in the mode space. The first equation is very simple. It's just an harmonic oscillator driven by the activity. But the second equation is this one. You can see it couples four modes through this operator. And this operator is just a geometric operator that use all the pairs of modes. So you have to sum this over all the possible pairs of combination of P, Q, L, K, which are the number of the modes. Of course, you cannot do anything with this, except notice that it's zero if the modes are not perpendicular by pair and are not maximally extended. So no coupling in that case. So the physics of the coupling requires modes that are extended and locally perpendicular. Okay. Let me skip this because it's late. Just notice that this and this is the same, this and this is the same, so we understand something. That's the message of this slide. But not all, as I said, I was honest. The coexistence. Can we do something to understand the coexistence between this regime where it's actuated and this disordered regime? Because it seems to be at the core of the fact that the transition is complicated. Well, you can take your equation and try to do hydrodynamics, or let's say elasticity. So you want to constrain the fields. So you constrain the fields, you write down the constraint equation. The first one was a linear equation, so it remains the same. The second one was nonlinear, so now you have closure terms here. This is now elasticity, linear elasticity. You can play with this, and at least you obtain that there is coexistence in phase space of solutions that are disordered, homogeneous, and solutions that are fully magnetized, that coexist in phase space. So they coexist in phase space, so it's likely that they will build front in real space, but we don't have all that yet. Okay, I think it's time to conclude. I played with toys. But this same year, a few months later, in the same journal, came out a paper with people playing with bacteria. And I showed you this regime. And here there is 1 million bacteria, not these 50 guys. And these bacteria are embedded in an elastic matrix. And they do exactly the same dynamics. Now, what is even more amazing is that I showed you that one. They changed something in the soup of their bacteria, and they do that. So we got convinced that these bacteria are self-propelling particles trapped in an elastic matrix. They show in their paper that they cannot move away, but that they can still reorient. I bet it's the same story. Now, we were so much convinced that in their paper, they showed that they can transit from one of the regimes. So here you see they are more like doing this local oscillation, and then they tune what they call the activity, so probably the amount of food, and then up, the system switch to the other portion. And because we understood something and we know what are the dimensionless parameters, we thought, okay, we should be able to do the same by tuning the tension in the springs. Because when you tune the tension in the springs, you shift the eigenvalues of the dynamical matrix. And so we should have something like this. So we cooked a very, very thoroughly modeled system, admittedly. But here you have this local oscillation. And now we are gently pulling. So now, I guess my student was really talented with 6 hands. He was pulling isotropically on the system. It was kind of a Shiva student. And he pulls very gently. And up. The system shift to the other dynamical rhythm, which demonstrates that indeed we have captured what's going on in this systems. Even if, theoretically speaking, we don't have the full nonlinear selection mechanism. These people less. Okay, I should conclude here. This is just a summary. I think one message is that tools of hard condensed matter physics are important here. I mean, there was a bit of group theory. I didn't enter into it. We have to project on modes. I mean, it's not like standard soft matter liquids. Here are the papers that you can have a look at, and I'm here only having want to discuss further. Thank you for your attention. Sorry for being a bit long.
Thank you very much for Thank you. Once again, what is there? We have now time for further questions.
So not really. You mean, I mean, what part? The one with the little disc? Yeah. Or the one with the springs? Both. Springs. No, not really. Actually, here I don't have videos, but you can change the lattice. Actually, I showed you with the Kagome lattice, it was already different. But we played with square lattices, and the main feature that is transition to collective actuation resists the shape of the lattice. As long as we deal with mechanically stable lattice. If we start with lattices which have inside zero modes, some which have more zero modes than just the translation and the solid body rotation, then you will send the energy to the zero mode, because that always happens, and you will have another story. I don't know. So the bacteria is not my frontal system, so but I think they are trapped enough that these zero modes are not there. And you see, it's very dense at the end. It's a solid. So the problem is the bacteria, you cannot track the bacteria. There are so many there, in the PID, etc., but you don't see individually the part of the bacteria. So I've been discussing with the authors that I met since then. We try to look more specifically at the dynamics of the bacteria by really looking at the microscope. It's easy to look really what the bacteria are doing. Yeah, because I guess the big circular. Yes. That's why but the question is at what scale is the circular motion? And I mean, in a crystal, you can imagine a collective oscillation. I mean, if you have a wave, the wave can drive you quite away from your reference position. What matters is that you come back. Okay, thank you. Thank you for the very fascinating talk. I would like to come back to the crystal. Yes. And you were creating these effects. And I would like to try to understand what is different in those effects when you would compare with the solid, let's say, no active matter. So you start with something that is like what, a single domain, I would say? Yes. And then create these effects? Well, I don't really. That's, well, you can think of this one if you want. Or I don't know which one you want. Maybe yeah, even here. Here, yes. So here you start with a single well-defined domain. Yes. And you remove particles. So there you create geometric frustration, even at equilibrium you will get defects. And here they are the same, as a matter of fact. When you don't remove too many, It's essentially the same physics.
And then they localize. So the difference is that when they are active, they can simply move.
Exactly.
And then it's very easy to create these domain boundaries. And
Exactly. Exactly.
So it's,
Exactly. And so some people have studied more detailed defects in active crystals. And so you can see that indeed the motion that already exists in standard crystal, where you have diffusion perpendicular to the direction of the declination, here the diffusion motion becomes ballistic. That's the main difference.
okay.
And so you can relax long distance.
Very interesting topic, really. And I would like to ask you a couple of questions. One is, I don't understand in your system when you say linear stability.
Yes.
You still have to keep some forcing to have this stability.
Yes.
And the fact that there is no noise.
No, when I studied theoretically, I first start by removing the noise. I look at the deterministic equations, and I really look them as the dynamical systems.
So the only new thing with respect to let's say system is the torque, of course.
Yes.
That's the one that creates this.
Yes.
But when you say mode selection, this is aside from the linear stability. This is something that you observe.
Exactly, and that I don't get from the linear stability analysis.
Okay.
I see taste of it, in the sense that the most unstable fixed point are the one with the maximal projection of the modes, etc. But again, it's only taste. The selection mechanism is truly nonlinear, and I don't understand it, of course.
Because that's only the decision.
Yes.
Okay, and the other is about when you pass to the continuum setting, you can pass to the continuum setting. And probably also in the discrete setting, but maybe it's easier in the continuum setting. You can calculate maybe the entropy field.
Yes, but we have not done that yet. So the continuum setting, we are just starting. One reason being that are those continuum equations really the correct one? Because of course you have to, when you constrain them, you make some truncature, so they respect symmetries, etc. All this is done. But for the moment, we are on the point where we test them. So we do simulation of this continuum equation, we compare them with discrete large-scale system things. And once we will be sure of them, we start following this path. Exactly.
So the idea was that all these large flows is related to the entropy production that localize.
Absolutely, yes.
Thank you.
That's what I expect, but I want to be sure first of the set of equations.
Very nice and simple scenario to study that.
Yeah, so your system is calculated by 2 length scale.
Yes.
What will happen if you use a time scale, like for example, with a CR deformation or a periodic deformation?
Okay, so that's another. So two directions of research after this first thing. The first one is no external forcing, nothing. The question of the continuum limits, the question of the transition in noise, because here I describe the transition in the actuation.
Yeah.
But the fact that we see the system experimentally demonstrate that it resists a finite amount of noise, but we did simulation as a function of the noise intensity, you can, of course, with a very large amount of noise, you will kill everything. So there is a transition in noise to be studied, but this is only meaningful in large systems. So one part of the field is going to statistical physics, continuum description of these new dynamics. The other part is to say, okay, but this is a solid. So what is the mechanical response of this bizarre solid? So you can concentrate first on the regime where you don't have the collective actuation, when it's disordered. And the first thing you can do is just look at the dispersion relation of the waves in that. So that's the first thing that the student is just starting. You know, we are in October, so November, so just starting. The second thing is just, hey, let's oscillate this stuff and let's see what's going on. And from here, you can immediately realize that the system will be very weird. Imagine you take this crystal, the elastic lattice, and you fix one side at a wall, and then the other wall you shear gently, even quasi-statically. You shear it, so because then you displace the nodes, because you shear. If you displace the nodes, the guy align with the displacement that you impose. So they will help you. Matter of fact, if you are strong enough, you can stop shearing, they shear for you, which means you have a negative elastic modulus there. Then you come back, but they are all against you. So you have immediately a very, very large positive modulus going against you. So the mechanical response of these materials must be everything ugly of all kinds. But I think it's interesting. So we start this, and we have started with just one particle that we just, so it's one particle in an harmonic potential, and we have attached another spring, and we do this. And already there, there are a lot of bizarre hysterical behavior for the reason I just gave, that it aligns with you, then there are resonance with the, it's already a huge story.
Any other question?
Well, have you tried this 3D somewhere in simulation?
Which, this?
Yeah, like instead of these spheres.
Changing the boundaries.
Yeah,
In 3D.
in 3D. Like,
No, yeah, okay, 3D. Okay, here I have to, so we can do simulation in 3D. But now the question is, okay, is how much relevant is it with respect to real system? All these particles are taking the momentum from the ground. And that's something very important. There is no conservation of momentum because they take it from the ground. So if you are in 3D, you will have to imagine they take it from something. So a real system should be some kind of a matrix from which you can take momentum. So it's not easy to really, and anyhow, even if you take the momentum from the matrix, if you start including the matrix in the description, the momentum is conserved again. So it's not very simple to imagine what would be a real system for that. But of course, you can do simulations. But we always try to you see that my work is always sticking with reality, theory, and numerics. But on the sphere, I mean, you can start playing with topology. We have people in the lab that study bacteria on the sphere. And this you can do experimentally. You can coin bacteria in a shell, and so then they are in a sphere. So why not? On a sphere, where there will be coupling to the curvature, etc., etc., well, plenty of things can happen, yes. But for the moment, I find it a bit complicated enough. You know, you don't always run for complication.
This is probably an out of basic question, but seeing that the same behavior is seen in the bacterial system, maybe in tissue.
So there is a movie that I have not included in this presentation, but so there is an experiment where they study tissues, and you can see that there is a regime where the tissues are rotating around the reference, the cells in the tissue are rotating around the reference configuration. They analyze it in terms of more like a nematic active liquids. I think it's wrong. If you have a reference configuration, it cannot be a liquid. So they describe this as vortices, and actually I don't think these are vortices. I think these are oscillations around position. But I mean, the community of nematic crystal is huge. I don't want to go too violent there. I think they are wrong. And I discussed a little bit with the experimentalists that they would like to agree with me. But I mean, they've been collaborating with important people in the field of nematic. So it's a scientific community, right?
And what about the heart also?
Yes, exactly. So the oscillations, etc. But there you touch a huge literature. And so whether there the oscillations that, I mean, it's typically an active elastic medium for sure.
Yeah.
There have been plenty of explanation of the synchronization, etc., etc. And I decided to look a little bit, but deep. I mean, either you go deep into this literature or you don't start touching
We
it.
need the equivalence of the torque.
Exactly. But the cells, okay, that's what's funny is that the same people in this nematic liquid crystal have this torque. They call it, in biology, it's called contact inhibition locomotion, CIL. If you look at CIL nature, you will see plenty of paper about this. It's that the fact that a cell, when it's hurting a wall, actually slows down, but also deviates. So there is a reorientation of the polarization of the cell because of an external force, which is essentially this. So the ingredients are there, actually.
Any other question? Okay, we thank
Let's
all
stop here.
here.